All right, so this is section 9.5. This is video 2. So we're going to actually go through the proof here, or I guess you would say the algebraic way of solving the logistic differential equation by using separation of variables. This is not an easy one to do, and as you can see, there's an entire page dedicated to this. Um, so just do your best, follow along. If you're not sure exactly what happened, you can always stop, go back, see what's going on. But we are going to be using some antiderivative techniques and some things that we saw in chapter 7. So we're going to need some of that, and then definitely some of our prior antiderivative techniques as well. All right, so the idea is we need to solve this for p. You do have to realize that, okay, so p is basically your dependent variable. Time in this case, or t, is going to be your independent variable. K and m are constants. You have to remember that k is it's kind of like your um, I don't know why I'm drawing up like constant of proportionality kind of a thing, and m is your carrying capacity. So those are constants in this case. So really it's just p and t that are variables. And as you can see, there's currently no t's in this at all. That is not that much different from when we did the exponential growth and decay models. All right, so let's get started. In order to do this, we want to separate the variables. So we need to multiply both sides by dt. Let's do that first. So I'm going to bring this over here, and this does take most of the page, if not all, in some more of the page. So dp equals kp 1 minus p over m dt. All right, we've got to get all the p stuff to the left. So we're going to divide by p. We're going to divide by that whole parentheses, 1 minus p over m. And you might have said, well, why don't we go ahead and distribute it through? Believe it or not, it's easier to leave it in this form, and you'll see why. So we are going to have 1 over, see, we're dividing by p. We're also dividing by the parentheses, so that's 1 minus p over m. And that's going to leave us, oops, don't forget the dp, have that still on the left. That's going to leave us with k dt. The right side of this is by far going to be the easier portion. All right, but the variables are separated. Okay, so I've got p's on the left, t's on the right, because there aren't any t's currently, so we can now integrate. Take the antiderivatives on both sides. Okay, so the right side, piece of cake. The left side, we're going to have to do some work. What you need to recognize is that I've got p's in the denominator, and those are both linear. All right, so let's do a little bit of work here. Let's multiply the entire top and bottom of the left-hand side by m. Multiplying the numerator by m, that really won't do much. That won't change anything. So we're going to have an m on top. But again, you have to multiply the bottom by m. So I'm going to write this, but then I'm going to erase it. If I have mp times 1 minus p over m, and I distribute that m into the parentheses, I'm going to get an m here, and then that m is going to multiply and get rid of the m in the denominator, so we're going to have p only. So we should have m minus p when I distribute. So really, what I'm going to have here is p still on the outside. Multiplying the m through, we get m minus p. Then I've got dp, and I've got k dt, and we are still integrating that. Okay, that makes it a little bit easier. From here, what I have is two linear functions of p in the denominator. Well, this means we're going to have to use integration of partial fractions. Excuse me, integration, yes, by partial fraction decomposition. So up here, on the right, I'm going to take m over p, m minus p, and we're going to decompose that fraction. So we're going to have a over p plus b over m minus p. Multiple ways you can go about doing this. I'm going to take the easier route. I'm going to multiply through everything by the common denominator, which is going to leave us with m equals a times m minus p plus b times p. And I'm going to choose specific values of p that's going to help us solve for a and b. So I'm going to pick p to be 0. I think that's an easy one to start with. And I'm also going to pick p to be m, because that's going to help us to find the values of a and b. Okay, so if p is 0, that's going to make the b times p go away, and that's going to give us m equals a times m. Solving for a, divide both sides by m, and we're going to get a equals 1. If I were to let p equal m, well, that's going to make the m minus p portion go away. It'll be m minus m. That's going to be 0. 0 times a is 0. So what we're going to get is m equals, I plugged m in for p, so we're going to get b m. And then once again, dividing both sides by m, we get that b equals 1. So now we have a way to separate our fractions here. Let's go back to blue. So we're going to have 1 over p plus 1 over m minus p dp, and we still have equals k dt, and we are still integrating. Now what we have on the left-hand side are going to be natural log antiderivatives, which is the whole purpose of doing what we just did there, to make it easier to take the antiderivative. So now on the left-hand side, we will have the natural log of the absolute value of p. Have to be careful because that's 1 over m minus p in the denominator, so that minus down there is going to end up giving us an extra negative out front. So it'll be negative natural log absolute value m minus p. Don't need the plus c on the left. I'm going to put it on the right, and on the right side we literally just get kt, oops, shouldn't put that in parentheses necessarily, plus c. All right, so now we're going to use some properties of natural logs because we're still trying to ultimately solve this for p. So I'm going to combine the two natural logs. The two natural logs are being subtracted, so the arguments can be divided into one natural log here. So we're going to get the natural log of p, oops, that's a big P there, over m minus p, and the absolute value still equals kt plus c. All right. I'm going to want to do something with the order that that p is in the denominator. So I don't know, maybe there's probably a better way to this, but I'm going to multiply everything through by a negative. Negative natural log absolute value of p over m minus p equals negative kt minus c. Technically, you could probably leave that as a plus c because it's just going to be a plus negative c. Doesn't matter. All right. Properties of natural logs. If I were to take the negative out in front of the natural log and make it the, oops, what happened there? Make it the exponent. So basically, bring this up here to make it the exponent of this thing, raise it to the -1 power. All that's going to do, if you raise something to the -1 power, is it reciprocates your fraction. So that's what we're going to do. Now we're going to have the natural log of m minus p over p. The right side stays negative, didn't do anything with that. So we've got that there. Okay, now we've got to get this p stuff out of the natural logs argument. So we are going to exponentiate both sides of the equation. So let's go ahead and do that. We're going to exponentiate both sides. Okay, so exponentiating the left will leave us with m minus p over p. Exponentiating the right is going to leave us with e to the negative kt. Technically, this will be times e to the negative c power. All right, I'm going to do something with that e to the negative c power. This piece right here. We do know this is going to be some kind of a constant. Technically, I'm going to bring this up here just to make sure I have a little bit of room. This is going to be the plus or minus e to the negative c. Again, remember, this is going to be some kind of a constant. So this whole thing could be positive, it could be negative. We don't know, which is why I put the plus or minus out in the front. We're going to call that, whatever that is, we're just going to call it a. We're introducing another new variable. I know, kind of a mess. And the question is, how do we find a? Okay, I'm going to come back to that when we're done solving the rest of this problem here. And we're going to come back to that. So now what we have down here, we've got m minus p over p equals a e to the negative kt. All right, we still want to solve this for p. Let's go ahead and divide the left side. We're going to split up that fraction, divide everything by p, so we're going to get m over p minus p over p, which is 1, equals a e to the negative kt. All right, we're getting there. We want to add 1 to both sides. M over p equals a e to the negative kt plus 1. All right, I am going to change the order on the right-hand side. I'm actually going to throw this 1 out in the front of the a. And I'm also going, well, no, let's just do it in 2 steps. So it'll be m over p equals 1 plus a e to the negative kt. Have to get that p out of the denominator, so you can either choose to multiply both sides by p and then divide everything, or we can just reciprocate both sides, which is what I'm going to do. So I'm going to reciprocate, so it gives me p over m equals 1 over the entire thing. And then the last step to solve for p, we multiply both sides by m, which really just introduces an m on the numerator on the right. So we get that the population equation is m over 1 plus a e to the negative kt. All that stuff is in the denominator. Okay, this is the equation. Okay, and if you actually peek to the next page, you would see that that's where that is. All right, but how do we deal with this a? What is this a? How do we find this? We know that technically it's the plus or minus e to the negative c. That's part of what we just defined it to be. But what is that? Well, the way you find a is that if your population equals your initial population, so basically if we say, okay, we're going to let the population be our initial population. Well, if that's the case, then the time t is 0, correct? So if time t is 0, that makes the whole left side, that makes this piece right here go to 1. And if the population is the initial population, then what you ultimately get is a equaling m minus p sub 0 over p sub 0. Basically plugging p naught or p sub 0 into the p's here. So that's what A actually is. A is the carrying capacity minus the initial population divided by the initial population. So A itself is not actually the initial population, but it's helpful because you need to have the initial population in order to find that value of A. It's kind of an offshoot of the initial population, but it has to do with the carrying capacity. So that's how you find A. Okay, and you will need that. Now, do we want to go through this process every single time we have to solve a differential equation that is logistic? Of course we don't. That process just took a long time to go through. We want to make this a little bit easier, and as much as I hate to say it, memorization here is going to be your best friend in this. What you really need to know is that the population equation is what we just said it was. That's your population equation. You need to be able to figure out what A is. You need to know what the carrying capacity is. And in some form, this stuff has to be given to you. And then, of course, the K value. Okay, that has to be given to you in some form. So in our example, this is what we're going to do. We're going to take a differential equation, which is given to us right here. And instead of doing the whole process, we're going to use the information that's here and be able to figure out what the population equation is. Okay, so again, they have to give you some of the pieces of information. They gave us K. Okay, that is right here. Now you do have to know that that's where it is in the initial in the differential equation. That's your K value. We know that this right here is your carrying capacity. That's M. The only other thing we need, because we need to have K and we need to have M, we need to have A. And in order to have A, you need the carrying capacity, which we have, and you need the initial population, which they gave to us. All right, so let's go ahead and figure this stuff out. We have K. K is 0.08. We have M. M is 1,000. What we need is A, but A is defined to be M minus the initial population, which is 100, divided by the initial population. And let's see, 1,000 minus 100 on top is 900, divided by 100 works out to be a nice, easy 9. They do not always work out that way, but in this case it did. So now we have everything we need to write this population equation, and then we can use that to find the population at 40, find the population at 80, and then be able to solve for when the population is going to reach 900. So let's first of all just write our population equation. So the population at any time t is going to be, according to our model, it is the carrying capacity on top, divided by 1 plus the A value, which is 9, e to the negative k, so that's going to be negative 0.08 t. There is our population equation based upon the differential equation that was given to us. Now, in order to find the population at time 40 and time 80, that's pretty easy. We're just going to plug in 40 and 80 and see what we get. Again, I am not going to run through the calculator work here. Hopefully this is something that you can do on your own. You'll plug in 40 for t, and you should come out to about 731.604. We're going to go with our 3 decimals here because we don't know what type of a population this is. Obviously, if this is people, you would round or something like that. But population at 80, same idea. Hopefully, you all know how to use your calculator. You don't have to retype the entire thing in. You just copy and paste the piece that's already in there and then type in 80 where the 40 was. You should end up with 985.266. Okay, and what you should be able to see, again, is it's 40 at 731 point something, at 80 it's 985. The further and further we go with our times here, the closer and closer this thing should be reaching towards 1,000. It should approach, but it never really should get to 1,000. If you plugged in a really big number, of course, it might slow your calculator down, but you should be really close to 1,000, like 999 point something. Last part is asking us, at what time does the population reach 100? Well, excuse me, 900. So in that case, we're going to plug in 900 and set that equal to 1,000 over 1 plus 9 e to the negative 0.08 t. Okay, again, multiple ways you could go about doing this. I guess we can go through it real quick here. It should take about a minute or so. We're going to reciprocate both sides because we need to get that t out of the denominator. Multiply both sides by 1,000 is going to give us 1,000 over 900, which is 10/9 reduced. Subtract 1. Subtracting 9/9 from 10/9 gives us 1/9. Oops, not e times e. We'll divide both sides by 9, which is going to give us 1/9 divided by 9, which is 1 over 81. Now we have to get the t out of the out of the exponential, so we'll take the natural log on both sides. And we are going to get the natural log of 1 over 81 equals negative 0.08 t. And then finally, we'll divide by negative 0.08. So our time is going to be the natural log of 1 over 81 divided by negative 0.08. which is approximately, using the calculator, 54.930. All right, plenty enough on this last one. Hopefully that makes sense. Again, if there's something you didn't get or it went too fast, go back and rewatch it, pause it, do whatever you need to do. But that's the basics. Again, you don't want to have to resolve the differential equation every single time. You just want to know how the pieces fit together, what parts go where to be able to go back and forth. All right, that's it.